Hi. In this session, we'll be selecting a dedicated outdoor air system, means a fresh air handling unit for ventilation for our projects. It's a 90-ton mixing equipment, means 90% fresh air return will be mixing with the 10% of atmospheric air, and we will be treating and conditioning it. Then we will be delivering it to the spaces as fresh air. So the central cooling coil selection and heating coil selection have to be done by the help of HVAC software. At the same time, we'll be doing it by the help of psychrometric chart as well. Okay, let's start. For example, in our building, nearly our fresh air demand is 2,655 liter per second. And we are taking like a 2,410 liter per second that's exhaust. Okay, actually this machine that we are going to propose is a heat recovery unit only. But instead of heat recovery unit, if it is a FHU, by mixing only it is achieving. Correct. Means 2,410 liter per second of exhaust that might be having a temperature of 25 or 26 degrees Celsius. That will be mixing with the fresh air of 2,655. Accordingly, the temperature of 2,655 fresh air will be decreasing. So when it is entering into the main cooling coil capacity we can decrease. By mixing, how we can calculate this FHU, that we can do first. Okay. And it is not 100% FHU. If it is a 100% FHU, in the psychrometric chart class, we have studied how to size a 100%. We can plot outside and inside plot in the psychrometry, then we can calculate everything. But this is by mixing only, how we can do that. And how I'll be selecting HVAC. By the help of HVAC, we can do it. Okay. So let me select our project. I'll be selecting our project. Okay. Okay. Let's go to system. Let me select. I'll be going to space. And in the space, I'll be creating a new space. Let's say I'm going to size my FH, fresh air handling unit. Okay. Fresh air handling unit. And what's the percentage? Percentage of mixing. You know, that is our exhaust is 2,410. Fresh air demand is, we have calculated already, no? Fresh air demand we have calculated. Positive pressurization also we did. So that's why we will be getting exhaust of 2,410 divided by fresh air of 2,655. 90.7. Let's say 10% mixing or 9.3% mixing. Let's say 10% mixing. 10% mixing we are having. Okay. So select this one, FHU, 90% return, 10% mixing. Whatever the floor area, doesn't matter. So what I'm doing means all these things, I don't want to give any input there. Okay, I don't want. Rather in the general, outside air ventilation requirement, this one, instead of liter per second, I'll be selecting that as liter per second. And the fresh air demand I'll be providing there, 2,655. Okay. Click OK. Before that, I will be going to the ASHRAE climate data. Abu Dhabi is the location that we are dealing with. What is Abu Dhabi location? Let me select it. I'm going to the map. That is Abu Dhabi. Okay, let me. Dhabi. And I'm selecting Abu Dhabi. Okay, Abu Dhabi, Dubai, Sharjah. I need Abu Dhabi. Abu Dhabi International. This one I'm selecting. We know, as per this only we have selected our data. And for cooling, annual heating, annual cooling for 0.4%. You know what is 0.4%? It means 0.4% of 365 days. This the temperature will be existing. Means nearly remaining 1.46 days or 35 hours. The temperature will be higher than 45.1. But when we are proposing an AC machine, the temperature that is existing minimum 0.4% of 365 days we have to select. That's why I'm selecting 45.1. And we have selected 23. Based on this temperature only, we have set the weather data, right? 45.1 and 23. Based on this, I'll be creating my system. Okay. So I'll be going to the spaces and system. I'll be creating a new default system. Let's say that is my fresh air handling unit, FAH. I'm keeping that as undefined. Under the system component, okay, dehumidification I am selecting. Dehumidification I need 50%. Correct. Means what is the relative humidity set point? I need 50%. And in the ventilation, instead of airflow control, instead of constant, I'll be selecting demand control ventilation. And after that, what's the base ventilation rate? 90-10 only. So 10% mixing. 90% mixing, 10% base ventilation. So I'll be selecting this as 10. Okay. And I'm just going to the zone component. FAHU 90-10 I'm adding. Under the thermostat, okay, anyhow, available thermostat I'm providing, or I can create.
Time is not mandatory, so I'm just providing that is my FAHU thermostat. Okay. And under the zone component spaces, I have already added thermostat. Sizing data, sensible safety factor you can assign now. For time being, I'm not assigning any safety factor. We can assign that later. Click OK. And you can right click this one, print and view design result. You can find the FAHU capacity. Okay. 2000. What was our demand? 2655 liter per second without any safety. Total coil load is 6.8 kilowatt. That is too less only, because why it is? If it is a 100% mixing system, means the machine will be taking 2655 liter per second directly from the atmosphere at a temperature of 45.1 degrees Celsius. Then it is cooling to room condition. Then the load will be very high. But we have selected this as a mixing, right? Instead of mixing, in the system component, this one you can select the constant flow rate. Then when you are generating this one, print and view design result, you can see your coil capacity will be 67.8 kilowatt. That is too high. Why? It is not mixing. Always the machine will be taking the fresh air from atmosphere. There is no mixing. There is no mixing. First one, outdoor air. Second one, cooling coil outlet. Fan outlet, room air. There is no mixing condition. That's the reason. 100% fresh air. So we need a mixing. It is mixing with the fresh air. How much it is mixing with exhaust air? 9.3%. Let's say 10%. That's why we have selected under the system component ventilation air, that is demand control ventilation. The base ventilation rate is 10%. That's where our coil load is. Print and view design result review. Our coil load is how much? 6.8 kilowatt. That much only we have to select. Mix. Correct. 6.8 kilowatt. Fine. So you can go to the psychrometry. Yeah. Now you can see the mixer air condition is there. Mixer air. It is mixing. That's why reason it is decreasing. But okay. Right click. Print and view design result review. Fine. So when you can go outside downwards. All the heat load is 0 except ventilation. Correct. This is ventilation. Our base ventilation rate is just 266 liter per second. Ventilation air is 266. Because remaining everything is which one? Mixing only. Mixing. 10%. See, now, but some countries will be recommending, instead of this temperature, for FAHU sizing, you have to go for this one, the second one. Means not this one, cooling condition. Instead of cooling dry bulb and mean constant wet bulb, you have to go for, because in this scenario, we can see the distance between dry bulb temperature and wet bulb mean constant, average wet bulb temperature is too less. Right? Nearly 2345, 22.1 degrees Celsius of difference is there. So that's why the difference between dry bulb temperature and wet bulb temperature is more. There is not difference between DBT and WBT that is representing a relative humidity 100%. 100% relative humidity means atmospheric air is having maximum quantity of water vapor in it. It can't hold any water vapor further. Correct. So that's why, but you can see here, the difference between dry bulb temperature and mean constant wet bulb temperature is nearly 22. So it is clear that relative humidity in the atmosphere is less in this scenario. Relative humidity in the atmosphere is less means latent heat in the atmosphere will be less. Definitely 45.1 will be your atmospheric condition. 23.9 might be the temperature you are designing for your room, means 24 degrees Celsius. Temperature in the HAP we will be giving 23.9 degrees Celsius, correct. 23.9 degrees Celsius might be the temperature we are assigning in the thermostat, correct, occupied condition. So that's why this much sensible heat the coil has to remove. Sensible heat might be more, but latent heat will be less there. So that's why, but in this scenario, evaporation condition, you can see 0.4% of year. Means out of 365 days, 0.4% means nearly 35 hours or 1.46 days per annum. This temperature will be existing, 30.6. Remaining 1.46 days, the wet bulb temperature will be higher than that. But that temperature might be existing for 1 hour or 2 hours. You don't want to select that. The temperature should exist at least 0.4%. Okay, here we have to consider wet bulb temperature. So when that wet bulb temperature is 30.6, on that time, the dry bulb temperature in the atmosphere will be 35.3. This condition we have to select for FAQ size because we can see the difference between DBT and WBT is very less there. So wet bulb temperature is too high. So it is clear that relative humidity in the atmosphere is too high. So relative humidity in the atmosphere is too high means latent heat the coil has to take care. So in this scenario, sensible heat might be less, but latent heat will be more. So coil has to take that load, no? So that's why whenever you are dealing with atmospheric air, ventilation equipment or cooling tower selection or evaporative cooling design, instead of this one, you have to go for this one. But this one will be only for ventilation equipment. So I will be changing my climate condition. So when in this condition, you can see when I am providing the weather data, 45.1 and 23, 45.1 for dry bulb temperature and 23 wet bulb temperature. I am getting how much? For FAQ 90-ton mixing, I'll be getting 6.8 kilowatt. But when I am changing, even if you can see outside the temperature is 45.1, I am going to change it to evaporation condition. Go to the weather property. And I'll be changing the summer design dry bulb temperature for evaporation is 35.3. Mean coincident dry bulb temperature is 35.3. And summer coincident wet bulb temperature is 30.6, 0.4%. 0.4%, that is 30.6. So relative humidity will be high there, 30.6. Okay. So atmospheric temperature is decreasing. So we might be thinking that the coil load will decrease. Check it. I'm just going to the system, FAQ, right click, print and view design result, preview this one. How much we are getting? Even if that is mixing, how much air is mixing there? But mixing is not live here. Check it. FAQ, zone component, yeah, demand control ventilation, that is 10% because we need that. We need that because relative humidity in the atmosphere is very high. Dehumidification 50%. Okay. Check it. You can see right click, print and view design result. Even if there is a mixing condition, the coil capacity is how much we need? 49.2. So that's why you should not sell because in every country it is not mandatory. When you are doing projects in high humid condition, especially in Gulf condition, air conditioning machine selection, we can use this value. Ventilation equipment, cooling tower selection, we will be using this value. Evaporative cooling, whenever we are dealing with the atmospheric air more, there we will be using this value. Okay, because there the relative humidity will be high. Machine, instead of sensible heat, latent heat in the atmosphere will be more. That we have to take into consideration. Because when you are taking this value into the consideration, latent heat will be less. So machine capacity for the ventilation will be less. Rest everything that will be fine. Ventilation load will be less when you are considering the cooling dB, this condition. So ventilation machine, you have to select with this condition. But both the condition, you have some countries, they might be saying anything. In that scenario, both the temperature you have to apply and you have to generate your report. Out of these two, which one you are getting the maximum, that you have to select. Because every country, evaporation condition and cooling condition, we will not be having this much difference. Some countries that will be less only. In that scenario, even cooling dry bulb temperature for both cooling, air conditioning and ventilation, you can use this value. But do both. Where you are getting the maximum, select this one. See, the same we can do by the help of manually also we can do. Manually, I will explain. Doubt you can ask in the last session how to do that by the help of a psychrometric chart. I'm going to select it, means this mixing condition, this FAHU for our demand, I'll be going to select by the help of psychrometric chart. Okay, so what is atmospheric condition? Atmospheric condition is 30 mean coincident dry bulb temperature, this 35.3 degrees Celsius. Okay. I'm just going to do that by the help of atmosphere, 35.3 cycle. Where is 35.3? Let's see, this is, let me select a linear. 35.3 dry bulb temperature line. 30, 31, 32, 33, 34, 35, 36, 35.3 somewhere here it will come. I will be making a straight line there. Okay, 35.3. Okay. And what about relative humidity is not there. Rather, we are having wet bulb temperature. Wet bulb temperature is 30.6. Fine. 30.6. So I'm selecting 30.6 WBT, wet bulb temperature, where it will come. You can see this is 25, 26, 27, 28, 29, 30. This is 31. So 30.6 somewhere here you can see how much latent heat it is having. So these are coinciding point. Okay. This point I'll be marking as a point number 1. Okay. Means that is my point number 1. Outside condition. Outside condition. Click OK. I'll be marking it there. Okay. That is my outside condition. So in this outside condition, I'm having this much humidity ratio. Correct. Means humidity ratio of outside condition. Each kilogram of air, how much we are having? Is 26, 26.5, 27, 27.5, 28. Each kilogram will be having 26, 26.25. 26.25. This much humidity we are having there. From this humidity ratio, we have to achieve to the room condition. Room condition 2450. I need 2450, but slightly 23.9 we have set in but psychrometry we can set it 24 degrees Celsius. Okay, so let me select 24 degrees Celsius dry bulb temperature, 24 dry bulb temperature, and 50% relative humidity. You know that point because we are having alignment circle there. That is my 24 degrees Celsius dry bulb temperature and 50% relative humidity. Okay. So let me select that is already the 50%, we know that is 50% RH. 50% RH. I will be marking a point there. In this point, how much humidity ratio will be there? We can check it 9 point something will come, right? Humidity ratio at outside condition. And that will be room condition. So this will be 8, 8.5, 9, 9.5. So this is, you can consider that is 9.25, slightly higher than that. Let's say 9.5, you can keep that. Slight variations, negligible, no problem. Or you can consider 9.25. This is 8, 9, 8.5, 9, 9.5. 9.5 is here only, but it is slightly higher than 9.25 as well. So that's why I'm rounding that into 9.5. You can remember that since it is constant. And what is the enthalpy of both the condition? Enthalpy of outside, this one only. So this point, see, for each point I'll be marking. So let me copy it, Control C, Control V. Okay. So this is my outside condition. Okay. Mark it. Control C. This is a condition I need inside. Okay. And so it is clear that from here to here, the load has to be decreased. Correct. So how much load has to be decreased? So I'll be taking a linear line or a total load line. Okay. Total load line from, or total heat line, or total load line, total heat line only, this one, this much heat I should remove. Okay. But as you know, if you are designing a 100% fresh air handling unit, you can mark the enthalpy of this point is H1, enthalpy of this point is H2. Then the total heat to be removed, mass of air into H1 minus H2. We know the volume of air, 2655 liter per second. So you can divide with the density, mass you can find. Then H1, H2 you can find. But this is not a total, because it's a mixing condition only. That's a mixing condition. And also, how the condition will come? From here, we have to cool it to the 100% relative humidity point. Then only the condensation will start. In the psychrometric class, already we have studied it. Then we have to cool it until this point of 13 degrees Celsius to achieve the humidity ratio. Up to here, you have to cool it. Then again, up to this point, we have to heat it as well. Okay. Then on what condition the machine will be entering into the cooling coil? What condition? For example, I'm having this FHU fan. Okay. And this is FHU cooling coil. This will be delivering 2655 liter per second. Okay. Let's say, correct, 2655 liter per second. And return will be 2410 liter per second. Remaining how much? 2655. 2655 minus 2410. That will be 245 liter per second. So 245 liter per second will be coming from the atmosphere. Mixing only. Then it is mixing. So that's why this 245 liter per second only will be having from the outside. Means 5.6 degrees Celsius dry bulb and that much relative humidity means 30.6 wet bulb. This air that is coming from fresh air return, this might be having less temperature only. When it is mixing with this one, overall the temperature of air will be decreasing. A lot of heat it will remove. So that's why mixing condition, how we can find it? We can find it. As you know, this is the total heat line only. Total heat line. Out of this total heat line, 90% we will be recirculating. 10% we will be mixing. So if you know the length of this line, or another way we can say, this is the total heat line. 90% of heat we will be recirculating. 10% of heat it will be coming from the atmosphere. Correct. Both the way we can, total heat line we can divide by the mixing. Accordingly, the mixing point we can find. This is a total heat line. 90% of this total heat will be overcoming by mixing. 10% will be coming from the atmosphere. So I will be dividing this line and I will be finding the mixing point. What's the length of this line? Length of this line, since it is whatever, even if it is not a scaled one, you can check it when you are placing your mouse pointer. This line is having a length of 56.22. See, it is not a scaled drawing. This is not a scaled drawing. The tool is plan shift we are using for quantity surveying. But just for class to plot the point and to scale it, I have taken this software. This one we are using for estimation only, no? Yeah. Anyhow, 10% mixing, the total length of this line, 56.2 meter. 56.22 meter. 10% of 56.22 meter is how much? 5.62 meter. No? So you can divide it. From this point, you have to divide it. So I'm taking a line. Okay. I'm taking a line. And from here, I'm placing my pointer like this. Mouse pointer like this. And after that, you can keep where 5.622 is coming. 5.6. There you can. place it. Otherwise, you can place your mouse pointer like this, then you can type it. Okay. You can type like a 5.622. Then click OK. That line you will get until then. But it is just reverse. Reverse means angle is not proper. That's the reason. But no problem. I will be marking it. We have to give angle, then it will come. But I don't know the perfect angle here. So I'll be selecting the linear. Okay. Let me select it. Since this line is 56.2 meter, 56.2 meter, I need a 5.62 line. So click here. Where is 5.62?
5.5, 5.62, 611, 62. Place it. So that is my mixing point. That is my mixing point. So I'll be selecting count, a mixing point. I'll be marking that here. Now you can find the temperature.
Means when we are mixing the air, on what temperature it will come. From this mixing point, you can make a line down. So what will be the temperature when we are mixing? The temperature when we are mixing, this will be like 24, 25. Correct. When it is coming to the machine will be delivering at a temperature of 24 degrees Celsius. When it is coming back after mixing, the temperature will be, this is 24, 25. Let's say 25.2 something will come. This is a mixing point. So only this load the machine has to take care now. Not finished. As you know, we have to cool it below the dew point temperature of this one. Correct. We have to cool it below dew point temperature of this one. Okay. So that's why I will be extending this line from this point to here. Means if we want to remove the relative humidity, correct, means from 26.25 to 9.5, this much relative humidity or this much condensation has to be done, humidification has to be achieved. Then you have to cool it until the dew point temperature. But even though the coil surface temperature, we can't keep 13 degrees. This is 13 only. No, this is 10, 11, 12, 13. We have discussed that. So that's why coil, this is the dew point temperature of 2450. But coil surface temperature, we can't keep 13 degrees Celsius. Why? Because the coil will be having a bypass factor. Even if at least 10% of bypass factor may come. So that's why, so 90% of air will be touching the cooling coil, that might be leaving at 13 degrees Celsius. And 100% relative humidity when it is leaving. But when the temperature is reaching to 24 degrees Celsius, the relative humidity will become 50%. But that's why, so 90% of 2600 or how much amount of air, let's say 90% of air will be leaving the cooling coil at 13 degrees Celsius. Remaining 10% of air will not achieve this 13 degrees Celsius. So effectively, by the effect of this 10%, when the air is leaving from the cooling coil, the temperature will not be 13 degrees Celsius. It might be higher than that. So that's why when we are considering the bypass factor, again, the dew point temperature has to be decreased. That's why you might have noticed in the report. Whenever now you can see the bypass factor is 0.1. Here you can see the bypass factor for this machine 0.1. But when the bypass factor, when I am increasing, the coil surface temperature, apparatus dew point temperature will decrease. Why? Because we have to decrease that. Then only the bypass factor effect will come. For example, instead of this 0.1 bypass factor, okay, the bypass cooling coil bypass factor instead of 0.1, if I am increasing that into 0.2, apparatus dew point temperature again will decrease because coil has to excessively cool the air to overcome that heat loss. Correct. Now just check it. I have increased this one. Now you can see instead of before it was 12.5. Since I have increased the bypass factor 0.2, now the coil apparatus dew point temperature is 12.1. Correct. So I am assuming 15% bypass factor for my machine. 15% bypass factor. So that's why this line, now as you know, if the coil is having 100% efficiency, when the air is and the coil surface temperature, if I am maintaining 13 degrees Celsius, air will be touching the cooling coil. when the air is leaving the cooling coil, the temperature will be 13 degrees Celsius. And this 13 degrees Celsius of air with 100%, because in this point, after achieving the humidity ratio of room condition, the relative humidity will be 100% only. After achieving this condition, the relative humidity in the room state will be, when we are reaching this point, the temperature and the relative humidity will be 2450. But that's not the scenario, right? Air will not leave at this condition. Rather, temperature of air when it is leaving will be higher than 13 only. Why that is? Why this difference is happening? It should be leaving. It should leave on 13 degrees Celsius. But in a real scenario, the air will be leaving the cooling coil higher than 13 because that is due to the bypass factor. I'm assuming 15% of bypass factor. 15, for example, I'm dividing this line again. This line, because this is a line, this is a point in which air is leaving the machine, cooling coil, and this is a point in which we have to achieve the room condition. So this line, what's the length of this line? 27.51. So 15% bypass factor I'm considering for this one. So 27.51. But this, when you are doing this calculation after taking the printout of psychrometry, you can take your normal 15 centimeter scale or a ruler you can use, not a roller scale you can use to mark this point to find the dimension. But this one, 27 point, how much I'm getting? 27.5. Correct. 27.51. So 27.51 multiplied by 0.15. How much I will get? 4.12. 4.12. So I'm taking a new line now. Okay. Where is 4.12? I'm clicking here and I'm marking a 4.12 line. Since it is trained, it will come. We don't want to give any angle there. 4.12 angle I am giving 0. We'll copy. Now this is a 4.1. Actually, this is a condition in which air is leaving the cooling coil. Means this is called a entering DBT line. Sorry, leaving DBT line. When the machine is this well, you can see the leaving dry bulb temperature. Leaving dry bulb temperature. Bypass factor we have discussed. It will be like a 0.15 is normal, but it can vary. It can up in the machine selection. We have studied it, right? When we are selecting the machine, we have already discussed in the HAB class. It can become 0.2 or it can become 0.25 as well. So with respect to the manufacturer, the bypass factor will vary. But when we are doing the design, you can consider 0.15. In the machine selection class, we have already studied what bypass factor can come. Correct. After doing the heating and the cooling load calculation, when we are selecting the machine, we have discussed regarding the bypass factor. For example, the machine is 51050. When you are selecting the first machine, medium low speed machine, 595 liter per second, bypass factor is 0.17. But the flow rate is increasing, that will become 0.2. For high speed machine, the bypass factor can become 0.26. So that's why it is not a constant value. Real scenario, it will vary. For initial design, you can consider 0.1 or 0.15. I'll be assuming 0.15. Real scenario, it will vary. Okay, this is a condition in which the air is leaving from the cooling coil. Okay. Okay, what might be the temperature there? We can find the temperature in this point. The temperature will be nearly how much? 10, 11, 12, 13, 14. 14.5 degrees Celsius will be the temperature in which the coil. Then what might be? This is the apparatus dew point temperature. This is not the apparatus dew point temperature. This is a condition in which air is leaving. Then the coil surface temperature. This is a condition of mixing. Through these 2 points, you have to make a straight line. Through these 2 points, you have to make a line. That line will be coinciding on your coil. This is your apparatus dew point temperature, ADP. That is your coil surface temperature, or that is my apparatus dew point temperature. I am marking it there. What will be the temperature? And from here, coil apparatus dew point temperature will come nearly 10, 11, 12 point something. Okay. Then what will be the coil capacity? Coil capacity is this much now. Means air will be, this is your cooling coil. After the mixing, the condition of air is this much. How much? 25.2 something, 25.2 something degrees Celsius. And the relative humidity of that state will be 50 and 50, 60, or let's say 55 degrees Celsius. On that state, air will be touching the cooling coil. And the cooling coil has to cool the air until this point. So that's why the humidity ratio has to be achieved as per this much dehumidification has to be done. Then from this state, we have to cool it until this point, and the process has to be continued until this point. So this is the coil capacity. This is the coil capacity. How much it will come? Check the enthalpy of both the point. Enthalpy of this point, we have to cool it until this point, 12 point, up until the apparatus dew point temperature. So the coil capacity of this much, let's say, I'll be marking there and here as well. There I'll be getting parallel to the enthalpy line. So enthalpy of this one and enthalpy of this one. Let's say this one I'll be considering as mixing. Okay, H1 for time being. And how much I am getting? This will be 50, 51, 52, 53. Correct. 50, 51, 52, 53 kilojoule. 53 kilojoule per kilogram of dry air. Fine. And what about indoor condition? Means coil until this point we have to cool it, right? So in that state, we need 30, 31, 32, 33, 34, 35. So 35. Okay. Now, what about the density? See, density of air, you can consider 1.2. Why I am saying even HAP software is also considering the density of 1.2 only for calculation. But accurate density, if you want to find, by the help of specific volume, we can do that. Okay. Here you can see air density, the software will be considering, HAP will be considering 1.2 only, standard one. Okay. But accurate density, if we need to find with respect to the psychrometric chart, we can find. Means on what condition air is, if you want to find the density, how we can find? We can already studied in the psychrometry. Specific volume we can find from here. Specific volume we can find from here as well. On what condition the air is entering into the cooling coil, that specific volume we should find. Specific volume of this condition. So specific volume of there is how much? Specific volume of that state is, this is 0.84 line. Okay. This is 0.85. And this is 0.86. So that will be 0.851, 852, 853, 854, 855. So somewhat very near to 0.86 only. So we can consider that as 0.859. Even if you are considering that as 0.86, because that is very near, no, that is fine. So that is my specific volume. So what might be the density of air there? Density of air. Specific volume I got. Specific volume is 0.86 meter cube per kilogram. Correct. Meter cube per kilogram. Meter cube per kg. Density will be 1 by specific volume. 1 divided by this much. So 1.16 kilogram per meter cube. We know the airflow rate, correct? So we know the airflow rate. Airflow rate is, supply airflow rate is how much? 2655 liter per second. But we need that in meter cube per second. So liter per second divided by 1000, we can convert that into cubic meter per second. Meter cube per second. Okay. So now we can find density is equal to mass by volume. We need mass. Density is equal to mass by volume. Mass is equal to volume into density. So we know the mass flow rate of air. M is equal to mass flow rate of air. M is equal to how much? Volume flow rate of air multiplied by density of air. So we are having 3.08 kilogram per second. Okay. Volume is in meter cube per second. So definitely the mass will be kilogram per second. Or you can calculate. Correct. Density is equal to mass by volume. Or mass is equal to volume into density. Volume is here rate only, meter cube per second. Density is kilogram per meter cube. So meter cube cancelled, kilogram per second. Okay. Now you can find what about the total heat has to be removed. Total heat has to be removed. This one. Mass of air into, or the coil capacity or total heat to be removed, mass of air into H1 minus H2. H1 we know how much? Mixing condition. So H1 I'll be assuming, I'll be taking from the psychrometric chart, H2 also. H1 is 53 kilojoule per kilogram, 53 kilojoule per kilogram of dry air, and H2 will be, okay, this one I'll be considering H2. Let's, any number you can provide, this is for class. H2, 35 kilojoule per kilogram. So I'll be considering that as 35. Okay. Now the total heat to be removed, mass of air into, that is, mass of air is this much multiplied by H1 minus H2. H1 is this much minus H2 is this much. So we need 55. What unit? Kilowatt, right? Mass, unit of mass is kilogram per second. Unit of enthalpy, kilojoule per kilogram. So the final answer will be kilojoules per second. Joules per second is called watt. Kilojoules per second is called kilowatt. The final answer we will be getting in kilowatt. So that is our coil capacity. So this is the way the FAHU has to be defined. In the starting classes we have studied in the psychrometry, that was not mixing condition. That was 100% fresh air. So when you are sizing the psychrometry, now the same I will be sizing by the help of HAP once again. All these parameters I am changing. Slight variations will come definitely. FAHU save 2655 liter per second in the space, 90 ton mixing, 2655 fine. And I'm just going to the system, FAHU, find system component, ventilation air, okay, mixing 10%, dehumidification at 50%, then cooling coil, bypass factor, I have considered 0.15. 0.15. And you can come to the sound component, the space, everything is fine. Thermostat, temperature 23.9. You can keep that as 24. Because why I'm making 24? I did on 24 here. Even if you are keeping 23.9, that is fine in the air conditioning design. I'm not considering any safety factors now, but in the final report, it will be good if you are considering 10% sensible, 5% later. Okay, click OK. Now you can generate the report, right click, print and view design result, preview that. You can see that is 47.7 we are getting. Slight variations will come definitely because manual calculation, HAP will be considering a lot of other atmospheric conditions and all. That's why this difference is coming. And also the conditions you can see, outside air, slightly it is decreasing, 34.7. And entering dB, coil entering dB. Coil entering dB, in our case, this is coil. Coil entering dB. In HAP is considering 25.1. In our case, coil entering dB, mixing condition. How much? This one. On this condition only the air is entering. How much it is? This is 24, this is 25. There also it is 25.1 only. 25.1. Coil entering wet bulb temperature. This point, what is the wet bulb? 15, 16, 17, 18, 19. Okay, so this will be 18.8 or 18. So in our case, by the help of psychrometry, that will be getting like 18 point something. 18 point. Why? Because HAP is considering the density value 1.2 kilogram per meter cube. I have considered a different mass only. And a lot of other errors will also come. Manual error. Okay. So this will come nearly 18.8 degrees Celsius of wet bulb. HAP will be considering entering wet bulb. How much it is? HAP entering wet bulb will be also 18.8 only. So fine. That is entering condition is fine. Mixing. Leaving dry bulb temperature, HAP is considering 14.3. Leaving wet bulb temperature is 13.5. What about our condition? In this one, leaving dry bulb condition, this one, coil leaving condition. Leaving dry bulb, this is 10, 11, 12, 13, 14, 14.4. In my case, even 14.3 is also fine. In our case, 14.4 degrees Celsius of dry bulb temperature leaving. And wet bulb temperature in this scenario, you can make, this is a leaving condition, coil leaving. This is 10, 11, 12, 13, 13.4 or 13.5, say 13.5. Even that is also same. Okay, then what else? One thing is there, because we are not going to achieve, because our intention is not by mixing the room temperature has to be achieved. In this scenario, when the air is leaving the cooling coil, the condition will be what? This one. What? 14.4 degrees Celsius relative humidity means 13.5 wet bulb
temperature. Relative humidity is 90%. But for fresh air handling unit, when the machine from the machine
air is leaving, we need 24 degrees Celsius and we need 50% relative. So definitely heating also has to be done. How much we have to heat from this point to this point, we have to heat it. Air will be leaving from here. From this point, we have to heat until 24 degrees Celsius. So once the air is leaving until this point, we can say that the condition will be 20, this much, which one? 24 degrees Celsius. And from 90% when you are heating, the relative humidity will become 50%. Okay, so heating also has to be done there. That's why here you can see central heating coil also they are providing. Why? Then only we can achieve that room condition, right? Heating coil is also mandatory. So what about the heating condition? This is cooling condition. Okay, this is cooling condition. And now we should find the heating condition. Okay, so I'll be marking further points in the psychrometric. For heating, let me select the enthalpy of this point because this is a condition in which the air is leaving the cooling coil. On that state, let me check the enthalpy here. Okay. Also, one more, and it has to reach until this point. There you can, the enthalpy is 48. 48. Okay. So let me copy Control C, Control V, Control C, Control. Okay. So this will be, I'll be marking that as H3 room condition. And this I'll be marking H4. H3 is how much? This one, you can see 48 only. Indoor condition, you can, already 48.
48 kilo
per kilogram. Okay. And here you can see that is, this is 38, 39, 40, 38.5. You can consider this as 38.5. 38.5. Okay. Now you can find heating condition. So H3 and H4. H3 is 48. H4 is 38.5. The unit will be kilojoule per kilogram of dry air. Now you can see the total heat. Heating coil capacity will be mass of air into mass of air. It is same only. Mass of air into H1 minus or H3 minus H4. This difference, correct? This difference has to be this difference. So H3 is 48 minus H4 is this much. That is 29.32 kilowatt. Correct. This is my manual calculation of FAHU design. And this is my HAP calculation of FAHU design. Definitely, when we are considering the safety factor, some other leakage factor, differences will come. Okay, but you should know how to do the manual calculation or how to do this one as well. Okay, now you can see what about the central cooling coil. In my case, for heating coil entering condition is this one. How much? 14.4 degrees Celsius. Heating coil leaving condition is 24 degrees Celsius. What HAP is doing? Heating coil entering condition is 14.3. Yeah, because this one only. 14.3 is fine. Heating coil leaving condition is 20. Correct. So this is a way mixing FAHU has to be selected. Correct. Now we have discussed 100% FAHU design that we are using in clean rooms. We have designed instead of 10% design, if it is mixing, if it is 20% mixing or 30% mixing, the same way only we are doing it. So we have discussed FAHU mixing condition by the help of HAP and the psychrometric. Now one more thing will come, a mixing by the help of heat recovery unit. So what machine that I'm going to propose in our project is not a normal FAHU, that is a heat recovery unit only. Heat recovery unit, pre-cool coil, pre-heat coil, that selection also is there. That we can discuss in the next session.